Hi everyone, I'm Professor Rad, and today we're going to talk about how you draw a conclusion when you make a hypothesis test. So the idea behind a hypothesis test, just as a reminder, is that you have a null hypothesis, something that you are told or that you believe or people assume to be true, and you are contesting that with an alternate hypothesis. Now, before I go into like the formal terminology and stuff, here's essentially what's going on. So somebody makes this null hypothesis about a population, and you're like, okay, I don't trust that. I'm going to go do my research, right? So you go out and you find some sample, and you get a sample mean. Now, if your sample mean is pretty close to that claim that's being made, then you're going to say, oh, you know what? It seems like that claim can be supported by my sample, so I guess maybe my suspicion was wrong. But if your sample mean is not very close to that mean that's made in the null hypothesis, then you might say, see, if that null hypothesis was true, this sample would not be very likely. So because I went out and I got the sample, this null hypothesis can't be true because this would have been so unlikely. It's ridiculous. So my alternate hypothesis is probably true. So because it's based off of the central limit theorem and probability, we're going to have some very specific terminology. But it's going to be based off of the likelihood that we would get a sample mean if this population mean were true. So let's fill in these formal terms here. It says when you conduct a hypothesis test, you're going to have one of two conclusions. Either your suspicion was warranted and you reject the null hypothesis. In other words, your sample mean is showing you no way this was true. So I reject you. I say, no, you are no good, null hypothesis, #rejected. Or if the evidence does not confirm your suspicion, in other words, your sample mean was pretty close to what the claim was, then we will fail to reject. The null hypothesis. Now, we're using this language reject and fail to reject because you can never prove a null hypothesis. And this is something that makes scientific communication difficult when you're publishing articles about things. So you can never prove, for example, that a medication will reduce the length of the flu by a couple days. But you can say, my evidence certainly supports that it does. And here's how I think of this. I kind of think of like a ridiculous example here. So I might make a claim like all people who wear glasses have blonde hair. So you might hear me make that claim, and maybe in that room you see somebody with brown hair and glasses. So you'd say, Professor Rad, your claim is silly because right here we have evidence that refutes your claim. So that's this first situation where you have evidence that shows that that claim can't be true, and you reject the null hypothesis. But then you might hear me say, okay, how about this claim? Everybody with rainbow hair has pink eyes. Now, rainbow hair is much less likely, so it's possible that in your sample or in that group you look around and you don't see anybody with rainbow hair. And so you're like, well, I mean, I'm suspicious, but my sample doesn't disprove what you're saying. It doesn't prove it, but it also doesn't disprove it. That's what's going on when we fail to reject a null hypothesis. So it could be that our sample just doesn't have the evidence in it to disprove the null hypothesis. It doesn't mean that the evidence isn't out there, but it does mean that our sample didn't capture it. So if you really are suspicious of that null hypothesis and you think there might be some sort of bias in your sample, then you could go out and repeat the experiment. And so that's one of the reasons why scientific experiments are repeated frequently, so that if you get the same results multiple times, then that's greater evidence that the null hypothesis has more truth to it. But you can't ever prove it because all of this is based off of probability and continuous probability. So we can reject or we can fail to reject the null hypothesis. And so the way that we're going to do that is we're going to compare a p-value that we're going to find. We're going to compare that p-value to a given level of significance. And in this particular font, this looks like an A, but it's actually a Greek letter alpha. So if you're writing alpha, it sort of looks like a little fish. That's how I think of it. It's the first letter of the Greek alphabet. In fact, the second letter of the Greek alphabet is beta. So that's where we get the word alphabet from. Alpha, beta, alphabet. Kind of cute. So our level of significance is going to be either alpha is 0.01 or alpha is 0.05. Here's what this means. So kind of when I was talking about this example up here, I was saying if your sample mean is close to the claim that's up here, then you may fail to reject the null hypothesis. But if the sample mean is kind of far away or unlikely to be happening if this is true, then that's when you would reject. So we need some way of saying, okay, when is X bar reasonably close to the mu that's given? And when is it suspiciously off? And that's what alpha does. So alpha says, look, if that null hypothesis is true, if the null hypothesis is true and there's only like a 1% chance that I would get the sample I got, that's weird. That's using the 0.01 level. You're saying if there's less than a 1% chance of my sample happening, then we're going to say that's significant. And that's when we would say X bar is too different from the claim, so we're going to reject the null. Or you could use the 5% level, 0.05, in which case you would say, if there is less than a 5% chance of my sample mean happening, that is unlikely, then we will reject the null hypothesis. So it depends on your field of study which level of significance you're likely to use. And there's also some talk in the scientific community currently about whether these two standards should be adjusted or changed. So typically you're going to see this 1% level more often in fields like biology or chemistry. And this 5% level you're more likely to see in fields like psychology or sociology. So to kind of summarize that conversation and formalize that terminology, if your p-value is less than alpha, your conclusion is to reject the null hypothesis because this is a statistically significant finding at the alpha level. And here you want to think of statistically significant as like bonkers, weird. So like if the population mean, if I tell you that the average temperature in New York City is 75 degrees over the course of a year, and you're like, I think not, and you go out and you find a sample, and your sample has an average temperature of 58 degrees, okay, you're going to say to me, Professor Ad, that claim is 75 degrees. If that's true, there's no way I would get a sample with a mean of 58. That would be insanely significant if I happened to get a weird sample like that. So I bet your claim is false. That's the situation here. You're rejecting my claim. If the p-value is greater than or equal to alpha, then you're going to fail to reject the null hypothesis. So this would mean maybe my claim was 75 and your sample mean was 73. And you do all the math and you get a p-value of like 0.001. And you're like, wow, if the mean temperature was actually 75, that would mean that there's only a 0.1% chance. Sorry. Wow, I misspoke there. So let's say the mean temperature is 75, you get a sample of 73, and you get a p-value of like 0.8. Okay, we want a higher p-value. So let's say you get a p-value of 0.8. That would mean, okay, if the average temperature in New York actually was 75 degrees, then there'd be like an 80% chance that I would get a sample with a mean of 73. So that's not significant. That is expected. Like I would expect to get this kind of sample if that were the mean. So I'm going to fail to reject the null hypothesis because my sample supports it. And it would not be significant at the alpha level. When we go to draw our conclusion, if the p-value is less than alpha, we again reject the null hypothesis because the results are statistically significant. And your conclusion is going to be whatever the alternate hypothesis was. Because you're rejecting the status quo, your suspicion is correct. If the p-value is greater than or equal to alpha, however, you're going to fail to reject the null hypothesis because the results are not statistically significant. And your conclusion is that whatever the null hypothesis says is likely true. It might be true. Again, we can't say definitively that it is true because you cannot prove a null hypothesis, but we can say that our evidence supports it being true. So let's look at an example of how I might ask you questions about drawing a conclusion. So in this example, it says, according to bestplaces.net, the mean household income in Utica is $31,048. Tom wonders whether those who live in Syracuse have a higher mean income than those who live in Utica. After he performs his analysis, a p-value of 0.41 is found. All right, so let's start out by stating the null and the alternate hypotheses. So Tom is comparing the mean household income in Utica with the mean household income in Syracuse. So he's challenging the status quo or challenging the assumption that they might be the same. So the null hypothesis here is that the mean in Syracuse would be the same as the mean in Utica. And his challenge to that is that those who live in Syracuse have a higher income. So his challenge would be a right-tailed test that the mean is more than $31,048. So now let's see what he can conclude. He does this analysis and he finds a p-value of 0.41. So in part B, we're going to compare those results to the 0.5 level. So off on the side, I always write something like a p-value versus alpha, and I always write p first and then alpha. His p-value was 0.041, and in this case, alpha is 0.05. Now, when you're comparing decimals, you want to think of it as like comparing words for alphabetical order as opposed to like lengths of things. Like, for example, the word cast is shorter than the word category. Let me rephrase that. Let's see. The word cast is shorter than the word carbuncle. I don't know. But carbuncle comes first because R comes first in the alphabet before S. So when I'm comparing these two decimals, they both start with a 0 in the ones place, a 0 in the tenths, but then the hundredths is where they're different. So that's where I'm going to compare them. And the 4 is smaller than the 5. So 0.041 is smaller than 0.05, even though it's a longer decimal. So when we go to draw our conclusion, we are in the situation now where our p-value is less than alpha because 0.041 is less than 0.05. So that means that the results are statistically significant. So are they significant at this level? Yes. So when the results are significant, we're going to reject the null hypothesis. And we can conclude whatever the alternate hypothesis said was true. So in this problem, our alternate hypothesis was that the Syracuse mean income is more than the Utica income of $31,048. So it says, can Tom conclude that those who live in Syracuse have a higher mean income than those in Utica? Yes, he can. So now let's say, suppose instead of at the 05 level, Tom was conducting this test at the 01 level. So again, I'm going to write out my p-value and compare it to alpha. Our p-value is 0.041. That was given to us up here. And now our new significance level is 0.01. In this case, when I compare the two, 4 is bigger than 1, so our p-value is greater than alpha. So if I go to see how I draw my conclusion, in this case, our p-value is greater than our significance level. That means these results are not statistically significant at that level. So are these results significant? No. In this case, we will fail to reject the null hypothesis. And we can conclude that whatever the null hypothesis states might be true. So in this case, if Tom is using the 0.01 level, he's going to say, you know what? The mean income in Syracuse might be the same as the mean income in Utica. They may be the same. So can he conclude that those in Syracuse have a higher mean income? Oh, this should be a 1 level. That's a typo. No, he cannot. Because we failed to reject the null hypothesis. So when you conduct a hypothesis test, you want to pay attention to what level of significance you're using, because you can draw different conclusions based on the level of significance that you use in the test. So typically this 01 level is considered like a stronger threshold to try and beat, because you're saying less than 1% chance is unlikely versus a less than 5% chance. So essentially what we're seeing here is based off of Tom's sample, his sample had about a 4% chance of occurring. So 4% seems pretty unlikely. And if you're using 5% as your threshold, 4% is less likely than that threshold, so that's why it was significant. But if you're using the 1% as your threshold, then 4% is not unlikely. So it would not be significant. So that's where I'm going to wrap up this video. In the next video, we're going to talk about some other considerations that might go into deciding which level of significance you want to do when you're conducting a hypothesis test. So I hope you found this video helpful in drawing conclusions, and I will see you in the next one. Bye for now, everybody.